Our next speaker is Marko Medvedev, yeah, from University of Chicago. Please join me in welcoming Marko.
Hello, everyone. I'm Marko. I'm a third-year grad student at U Chicago. I work with Nati. Today, I'll be talking about weak to strong generalization in random feature networks. Okay, so this joint work with a number of collaborators. So Kaifeng was here, Dingli, who's not here, Sanjeev, Zhiyuan was here, and oh, Kaifeng is here. Sorry. Okay, and Nati. Yeah. Okay, so weak to strong generalization. So this phenomena was sort of named in this paper, Burns et al. 2023 from OpenAI. They use this phenomena to study superalignment as a sort of some analogy. So superalignment is this question whether humans will be able to, well, teach some superhuman models to be better than them and, like align them to do what they want. And the analogy that they consider is two models where one is weak and another one is strong, and the weak model is trying to teach the strong model. And they call for theoretical understanding of this phenomena. And well, they really care about this because they gave a lot of money for people to study this. Okay, so it's an important research direction. Okay, so let's now introduce weak to strong generalization. Okay, so we have a teacher and a student, and the question is, can the student hope by learning from the teacher, who learns from some ground truth F star, can the student hope to be better than the teacher? Okay, so the teacher is trained by minimizing its error with respect to some ground truth F star. The student minimizes the error with respect to the teacher, so the student never gets access to the ground truth F star. Okay, but both the student and the teacher are valid with respect to the ground truth F star. Okay, so this is the general setup. And we will in a second see what we mean by weak and strong. Okay, so in the Burns et al. Paper from OpenAI, their weak teacher is a GPT-2 type model. Their strong student is a GPT-4 type model. And they pre-train both models, but then fine-tune them to for some downstream tasks. Okay, and they ask, can the student outperform the teacher? And well, they show that this is possible for a number of downstream tasks. If you will do some kind of engineering with something that's roughly equivalent to early stopping, where the student at some point starts reinforcing the thing that it learned and ignoring what it sees from the teacher. Okay, so in analogy to that, in our setup, we're going to consider two-layer neural networks, where the first layer is going to be, well, for the teacher is going to have, empty features. The student is going to have, well, for this talk, we're going to take number of features of the student to be infinity. Okay, and we're going to train the student, okay, with early stopped gradient descent. Okay, so just one thing, yeah, and okay, so we're going to take the first layers to be random and fixed. So this is just the, like the simplest thing that you can consider. Okay, and so we're going to draw the random features for the first layer from some distribution of features. Okay, and so here we're going to take, well, for example, we can take the teacher features to be drawn from some normal distribution and the student teacher to be drawn from the same distribution. Okay, and then we're going to train the student. Okay, and yeah, so before I get to that, let me first say that both the teacher and the student are going to be trained with the infinite data, essentially, so on population. Okay, so the teacher second layer weights are just going to be the argument of this function, so like the population loss of the teacher predictor. Okay, and so the first layer weights are going to be fixed and are going to be drawn randomly. The second layer weights are just going to be optimized over the population. Okay, and then we're going to get the teacher predictor. Okay, and then the student is going to be trained with gradient flow with early stopping. Okay, so this is sort of in analogy to what Burns et al. Does in their paper. Okay, so we just initialize gradient flow with 0 weights at the start, and then train the student until stopping time tau, and then we just do the gradient flow and population loss.
Just like a question. So how do you train like within infinite number of features for this?
I mean, you can just write down the equation in the function space.
Okay, so
yeah.
So you don't train it actually. You just...
Right. In the I mean, you're gonna see in a second. In the experiments, we're gonna take a finite weight student, and we're gonna train with the SGD. But to write this equation down, I can actually write it down. So in function space, F student at time t so F student at time t is going to be given by this LK, which is the operator given by the kernel of the student K applied to Ft minus F, so like the student predictor at time t. Okay, and then we're going to see very soon what the closed form of the solution of this, like the solution to this equation is going to be. Yeah.
Even enough of data where you train and where you train the student.
Yes. Yeah.
Fully random is really the random feature model in teaching.
Yes.
Everything else is fixed.
Right.
So really, the trajectory of the GD path where you train the student is really fixed, and that's a right. Like the only comes from the random feature in teaching.
Yeah. That's true. Yeah. Like the gradient flow path of the student is fixed once you fix the teacher. Yes. And once you choose your feature distribution.
It's like a gradient flow in function space.
Yeah,
like
this is the equation of the gradient flow in the function space. And this LK is just the standard kernel operator. Yeah. Okay, so are there any more questions about the setup? Okay, so for the purpose of the talk, we're just gonna think of the student as having infinite width, but we will see later in a second that this will approximate what happens when you train the finite width student with the SGD. Okay, so in this setup, we can now state two results that we have. So we establish we do strong generalization in the following sense for ReLU networks first. Okay, so if we take our data to be drawn from some normal distribution as well, and the activation function to be the standard ReLU function, then for any ground truth that's a fixed even polynomial, or more generally a sum of an even polynomial and a linear function, if we take the stopping time tau to be something of the order of log times the number of log of the number of teacher features, then the student loss is going to be smaller than the teacher loss, and it's going to be smaller in a sort of exponential way. So, sorry, in polynomial way. So the student loss is going to be the teacher loss to the power 1.49, and so I normalized the ground truth to 1. Okay, so the teacher loss is going to be something less than 1. So the student loss is going to be something even smaller than the teacher loss. Okay, so this shows that student loss over the teacher loss is going to go to 0 as the number of teacher features goes to as the number of teacher feature increases. Okay. Sorry. Yeah, tau is the stopping time. Yeah. And then we also consider linear networks. So if you take sigma to just be sigma of z to be equal to z, okay, and then now take x to be not from like the uniform Gaussian distribution, but from, you know, like to have some covariance. Okay, then if the target function is supported on the first k coordinates of x, so beta I has zeros for I greater than k, okay, then and then we take the dimension of x and the number of teacher features to be in this relation. Then if we take the stopping time to be some constant times log number of teacher features, then we're going to get an even bigger separation here. Okay, so here we also normalize the ground truth to 1. So the student loss is going to be quadratic in teacher loss. Okay, so teacher loss is something less than 1. Student loss is going to be something quadratically smaller. Okay, so the loss of the student over the loss of the teacher is going to go to 0 as we increase the number of teacher features or this like dimension of x. Okay, and so this establishes weak to strong generalization in these settings because the student is able to do better with respect to the ground truth than the teacher, even though it only saw the examples generated by the teacher. Okay, are there any questions so far?
So here k is some fixed in the second setting. The signal is based on some number of fixed signal features.
Yes, k is fixed. Yeah. I guess like the way I'm presenting the theorem statement here, we fix k, but you could, if you wanted, you could vary k as well, and then see what happens when k is varied. Yeah, so I mean, like our most general theorem statement is going to allow for varying.
Yeah. But here the O tilde is hiding k.
Right. Yeah. The O tilde is hiding k here. Yeah. And if you don't normalize the ground truth, then you would get some, you know, like dependence on like the norm of the ground.
You didn't tell us anything about LST. In other words, the loss between the student and the teacher.
Right. So the loss between the student and the teacher is just the population loss of like, yes, just like the expectation over the population of the distance between the student predictor and the teacher predictor.
I mean, in the theorem, like, is that also going to 0? Like, is that obvious? You told us the ratio LS over LT is going to 0. But is it true that LST over LT is going to 0?
No, so like you will see that, like I'm gonna say something about that very soon. So you're gonna see. It's gonna be clear when I introduce one picture soon. Yeah. And we also do some synthetic experiments here. So we essentially just generate the data in this setup, and then here in the first plot, we plot the gradient flow stop or like the stopping time with respect to the ratio of the student loss and the teacher loss. Yeah, and then here we plot the teacher loss with respect to the student loss. Okay, and then we take a finite width student. And then here in the second setup, we show a slightly different plot. So we show the ratio of the student and the teacher squared, the teacher loss squared. Okay, but here in the other plot, we also show the teacher loss versus the student loss. Again, this just slightly different notation because I did not change from the paper, but yeah, okay. And then essentially we see that for some sort of like optimal stopping time here, we always improve over the teacher, and the improvement is bigger for wider teachers. Okay, and so here we see that we're, for example, like more than 10 times better than the teacher. Okay, and then like the true coefficient here, when we just try to fit the student as a function of the teacher, is something like 1.55. Okay, but here we exactly get something very close to 2. Okay, and then we can see from this plot for the optimal stopping time, the ratio is very close to 1, which is what's predicted here. Okay, so the prediction for infinite width student holds for finite width student. And I mean, you can establish this formally as well. But I'm not going to talk about finite width students in the talk. Okay, so to understand what's going on here slightly better, let's consider this case of linear networks. Okay, and here I'm showing the variance of the features, and here I'm showing the ground truth in these directions. Okay, so the ground truth is gonna be spanned by some of these because I took a linear function, and we said it's gonna be supported on the first k. Here I'm showing k equals to 3. It's like on the first 3 directions. Yeah, then like the teacher is gonna learn some approximation of this ground truth. So, well, it's gonna get something maybe like relatively close to the ground truth in these directions, and then like something close to 0 in the other directions. So in particular, because the teacher has just like finitely many features, and it only says, like sees this in the error, is going to try to approximate in this subspace as close as possible, but then like it's going to get like some non-zero stuff in the other directions. Okay. And yeah, just a reminder, the student, since it's trained with the early stop gradient flow, well, we can sort of see how this gradient flow early stopping is going to look. So in particular, if I write down actually what the student kernel is, okay, so here I plotted how the student predictor looks compared to the target and the teacher predictor, and now I'm going to just show in a second how I got this plot. Okay, so let's consider the student kernel for a second. Okay, so I can write down the student kernel, which is given by this random feature distribution. And then I can rewrite it in terms of this basis. Okay, and we see that if I write it in terms of this basis, so now EK are just going to be some orthonormal basis with respect to this like student kernel, and we're going to see that actually, in this case, the base is just given by like the directions of xi, and the eigenvalue of the kernel operator with respect to this ek, which is going to be just one of the xi's, is going to be given by the variance of x here. Okay, so how does this tell me what the student predictor looks like? Well, I can solve the equation of the gradient flow in function space. So there's a closed form solution. Okay, so the student predictor after time t of this gradient flow, if it's initialized at 0, is exactly going to have this closed form. So this is just like very simple to solve because you can just write this as an ODE along each of the EK directions, or each of the XI directions in this case. Again, then so I can see that so these lambda k's are the eigenvalues of these eigenfunctions with respect to the kernel operator, which are just given by the variance of x in these directions. So if this lambda k is larger, then if I take some t, then this e to the minus lambda kt is going to be closer to 1 for larger eigenvalues. So the student is going to be sort of closer to the teacher in the directions where the lambda k's are bigger. Okay, so like in these 3 directions, because the lambda k's are bigger, for lambda 1, lambda 2, and lambda 3 are bigger, the student is going to be very close to the teacher, and then here it's going to be slightly further, and like it starts from 0 and it gets up to like some point that's going to be, well, further away than the first three directions. Okay, so now we can consider what does this mean for the weak to strong generalization. Again, maybe are there any questions so far? Yeah.
So if you had trained directly the students on the ground truth, you would have a similar effect.
Yeah, I mean, the student doesn't know, if the predictor is like the, like this, like what I just said about the student is independent of, this setup. It just holds for, like any target function that has this form. So yeah.
Yes. So then, and just to make sure I understand, you don't see any benefit of training on the teacher rather than on the ground truth. I mean, yeah.
Right. I mean, like, yeah. I mean, that's obviously true. Yeah. Like it's better to train on the ground truth, but the setup is that we only have access to the
distillation thing where I think there's this idea that if you have a big model, you want to distill it to a small model, then it's better to train on the big model than on the ground truth somehow.
Right, but I guess here you're going the other direction because you have like a ground truth, then a small and then a big model. It's but I'm not exactly sure what you could say about distillation using this. But yeah, maybe we can discuss later. But yeah, okay, so let me tell you what this means for weak to strong and how we can interpret weak to strong generalization in this setup for this picture. Okay, so as I said, the student predictor is going to be close to the teacher predictors in directions with the larger eigenvalue. Okay, so in order to, it's like, now the question is like, how can we choose the stopping time to make use of this fact? Okay, so I see here that if I choose, if it's possible to choose the stopping time so that a few of these first coefficients are very close to 1. So if I can choose the stopping time so that in the first few directions, the student is very close to the teacher. But in these directions, it's not, then I can effectively zero out these because, so if in these directions the student is not close to the teacher, it's going to be very close to the zero because we initialize the gradient flow from 0. Okay, so if I can choose the stopping time tau to be proportional to maybe a large eigengap, okay, then I can effectively zero out all these directions. Okay, because in those directions, I'm going to be, this expression is going to be closer to 0. Okay. Are there any questions about this? Okay, so this sort of gives the intuition of like the workings of the weak to strong generalization. So I can essentially just zero out the error in these unimportant directions. Yeah.
Because you don't do early stopping when you train the teacher model. If you do early stopping when you train the teacher model, do you still have this weak to strong generalization?
Right. So like if you do early stopping with the teacher, like the teacher error in these directions is going to be smaller. Yeah. So you're going to, I mean, you would still have weak to strong generalization if you assume that your target is spanned by like the first k directions, but yeah, it's going to be smaller. Yeah.
So let's say you choose the optimal stopping time for teacher and also choose the optimal stopping time for student.
Right, but because the target is spanned by the first k directions, the optimal stopping time for the teacher is actually infinity.
You're training the teacher on the population risk.
Yeah,
Right?
yeah.
Stopping isn't actually helpful.
Right, because we're training, yeah. So I mean, the principle applies, but the principle tells you that the optimal time is infinity for the teacher. So, yeah, I mean, I can explain this offline again, but yeah. Okay, so essentially, we can, with this principle, if we have a big eigengap, which I guess in this case I specifically chose it, so there is a big eigengap, we can zero out the teacher error in these directions, and that's how we can establish weak to strong generalization. Okay, so our goal from now will be to see if we can establish that a big part of the teacher error is in these directions. Okay. So the question is a large portion of the teacher error in the directions that are not included where the target, in the directions where the target is not spanned? Okay, so like here in like x4 up to, xd. And well, it turns out that this is true if, well, under this condition, and an additional condition that the teacher features are independent along the first k directions. And I mean, this is going to be true with probability 1 in our setup. So this part is fine. Okay, so here's a more general theorem. So we prove that under this assumption, if the teacher attains the minimum loss, okay, so like it's optimal, then at stopping time tau, the student loss can be bounded by, okay, something that's less than the teacher loss, so 1 minus kappa k times the teacher loss, okay, plus some, like additional error term. And for now, just focus on this first part, because as I'll show soon, this error term is going to be much smaller than the first part. Okay, and then so it's 1 minus kappa k times L teacher plus lambda k plus 1 squared tau squared L teacher plus something that depends on the ground truth and this stopping time as well. And then here kappa k is going to measure the alignment between the teacher features and the top k eigendirections. So essentially, if the teacher features are well aligned with the k eigendirections, then like smaller part of the teacher is going to be in the directions e greater than k, greater or equal to k plus 1. Okay. So essentially, if you ignore this term for a second, this theorem shows that at least kappa k times teacher loss of, like at least kappa k part of the teacher loss is going to be in these directions. Okay, and then so the student can essentially zero out that part, and that's where the weak to strong improvement comes here. Okay, so now let's just write this theorem with a proper definition of what kappa k is. Okay, yeah, just one comment here. So in this theorem, we can clearly see how the large eigengap can help here. So if I take this term, lambda k plus 1 squared tau squared, to be of the order lambda k plus 1 squared over lambda k squared, okay, then, and if the eigengap is large, so lambda k plus 1 is much smaller than lambda k, then okay, this term is going to be very small, so it's going to be like much smaller than this first term. So we're going to sort of essentially be able to just ignore this term here. Okay. So let me just now rewrite the main theorem and say exactly what this kappa k is. Okay, so let's go back to the student's kernel. Okay, so the student's kernel is can be written as, sum over these eigenfunctions ek. Okay, and then we also want to look at the teacher features. So the teacher first layer has mt features. Okay, and so I want to see how well these features align with the first k directions here. Okay, so we're going to introduce the following two quantities. So AL and BL are going to be just the matrices of the projection of sort of the covariance of these features projected on like E of the first L E's and the last from L plus 1 up to D E's. Okay, and then the kappa L, so it's going to be defined for any L greater than K, is just going to be 1 over 1 plus the largest eigenvalue of this matrix given by A and B. Okay, and it is a measure of the alignment between the teacher features in the top L eigendirections. Okay, and then so we define kappa L for any L greater than K, so we can actually write like a slightly stronger main result here. So we can actually take the infimum over all L greater or equal to K of this expression. So the previous expression was just a simplification of this expression. So yeah, this is just like a slightly stronger result. Okay, and sort of this allows us to well to establish like maybe the same result even if the eigengaps are sort of differently distributed than what I drew in this picture. But yeah, okay, we can we're gonna come back to the main theorem at the end. Yeah, are there any questions so far? Okay, so here we can also see the two technical difficulties. So the first technical difficulty is, well, to prove this theorem on the left. And well, the second technical difficulty is to bound this kappa L. So we said that kappa L, so if I go back, so kappa K part of the teacher area is going to be here. So you want this kappa K to be as close to 1 as possible. Okay, so the second technical difficulty is just showing that this is close to 1. So that this lambda 1 is upper bounded. So the largest eigenvalue of this matrix is upper bounded. Okay. And just a reminder of what we did here. So with this result, we established that the kappa K portion of the teacher is in the last, like the last few eigendirections. And using this theorem, we were able to establish these more specialized theorems that I showed for, well, for example, that weak to strong generalization happens for linear networks. Okay. And now let's just talk briefly about what this means for weak to strong generalization. Okay, so these are the two specialized theorems that we established from the general result. Okay, and the one measure of weak to strong generalization that Burns et al. Uses is this performance gap recovered. So performance gap recovered is the loss of the student minus loss of the teacher. So essentially how much the student improved over the teacher over what is the best possible improvement of the student over the teacher. So this LSC is just the student's ceiling performance, which is like the best performance that the student could theoretically have. But we don't necessarily need to we don't analyze this directly because we can just bound PGR as L teacher, lower bound PGR as L teacher minus L student over L teacher. Okay, and essentially you want PGR to be as close to 1 as possible. So you want to recover as much of this gap as possible. And so our results say that PGR goes to 1 as number of teacher features goes to infinity, but we actually say something even stronger. So PGR going to 1 only says that the student goes to 0 superlinearly with respect to the teacher, but it actually goes, like the 0 polynomially faster. Okay, so this shows that maybe performance gap recovered is not the best metric to use to measure weak to strong generalization here. So just to establish what we did so far, well, we show that we can have weak to strong generalization in random feature networks. And the strong student here is not pre-trained, so he does not have like any extra knowledge. So in the Burns et al. Paper, both GPT-2 and GPT-4 models are pre-trained, so they do have extra knowledge. And then teacher is trained optimally with infinite data. And as I showed previously, this is very closely tied to early stopping. So early stopping the student allowed us to establish that it zeroes out this noise directions. Okay, and then we show that PGR goes to 1, L student over teacher goes to 0 as the number of teacher features increases. But we actually established something even stronger. We established that in linear networks, the student is quadratically better than the teacher. And for ReLU, we established that the exponent is 1.49, but it's not exactly clear what the sharp exponent is. Again, well, this is all rigorous and with a small star, so we need the Gaussian universality to turn the result for the ReLU networks. So here we do have an upper, like we can write some upper bound for the student in terms of the teacher loss for the ReLU networks, but to turn that bound into this form, you need a lower bound of the teacher, and for that, well, we only know how to do that with Gaussian universality. Yeah, so that's the asterisk here, but the linear networks case is completely rigorous. So now let's go into the second section of the talk, where I will talk about one other aspect of weak to strong generalization in this setup, and that will give some further intuition about how things work here. Okay, so we see that for ReLU networks, we have exponent 1.49. For linear networks, we have exponent 2 here. So the question is this the best we can do? Can maybe student loss be like exponentially smaller than the teacher, or is polynomially smaller, quadratically smaller, the best we can do? Again, well, it turns out that yes, quadratic separation is the largest possible in this setup. Okay, so we show a lower bound on the teacher loss. So we show the teacher, on the student loss. So we show that the student cannot improve arbitrarily over the teacher. Okay, so essentially we show that in any random feature model trained with gradient flow in this way, the student loss is lower bounded by something that's quadratic in the teacher loss. Okay, so essentially you can have weak to strong improvement, but you cannot have arbitrary weak to strong improvement. Okay, so essentially this is tight for linear networks. And then we can actually slightly generalize this lower bound to hold in other setups as well. So in particular, we can take any teacher that's trained to minimal loss, and we can take any student that's trained with gradient flow on the, well, this should be LTS, so the loss with respect to the LST, loss of the student with respect to the teacher. Sorry, this is a type. Okay, and then we can even further generalize this. We can show that the lower bound holds for any shrinkage optimal teacher. So if you can shrink your teacher a bit and then get a better error, that's not allowed. Again, for any shrinkage optimal student, in the sense that, yeah, if you shrink your student a bit, you're going to get a better error. So those things are not allowed. So if this condition is satisfied, then the lower bound is going to hold. Okay, so this condition is more general than these two. And, you know, like from this, it falls sort of like any random feature model will train the gradient flow, satisfy this condition, hence it satisfies the lower bound. Okay, so now I'm gonna give some comments about the lower bound, and then I'm gonna quickly show the proof of the lower bound, because it's maybe instructive to see how things happen here. Okay, so if FT and FS are some effective hypothesis classes of the student and the teacher, so a crucial part here is that the 0 is contained in both the student and the teacher effective hypothesis classes. Okay, but we can sort of slightly relax this, that the student is minimizing the loss with respect to the teacher, and it's sort of bounded in like any norm. Okay, then so some of the implications of this lower bound is that in order to have the student loss go to 0, the teacher loss also has to go to 0. But if the teacher loss goes to 1, then the student loss must also go to 1. So maybe this is slightly unexpected, that there's actually, this like weak to strong improvement is like very limited in this case. And this is different than boosting because we have this limitation, and it's different than the weak to strong generalization showed in the Wu and Sahai paper from 2024. So they consider it classification and not regression. And in that setup, they show that even if the teacher has arbitrarily bad loss, the student can have arbitrarily good loss. Again, so their setup is different because their teacher is trained on a few samples and the student is trained on lots of samples, but we train both the student and the teacher on population. And their setup is different because the teacher and the student overfit, so they're not optimal in any sense. And here we consider that the teacher and the student are optimal, at least in this shrinkage sense. And so for this lower bound, it's crucial to have 0 be in this effective hypothesis class of the student. So if the student is specialized, so maybe like pre-trained to be very close to something that's away from 0, then we can avoid this lower bound. Again, for example, this other paper, Charikar et al., sort of is related to this case where the student is specialized, that is like pre-trained to something that's away from 0. Okay, so now I'm gonna briefly go through an outline of the proof of this lower bound because it's sort of instructive of how things work in this setup. Okay, so we're gonna consider everything projected onto a few of these eigendirections. Okay, so the target function is maybe just, we're going to take the target function to be, say, E1 here, just to simply be able to write it as just like one line here. Okay, and then the teacher predictor is going to be somewhere in this space. Okay, so I'm just projecting on like E1 and E2 here, I guess. Okay, and then so I'm now going to represent, so the teacher is going to be along some direction, but since it's shrinkage optimal, the teacher is actually restricted to be in some set. So again, this will be in like some high dimensional space, a sphere in some high dimensional space. So it's just the restriction of this shrinkage optimality in this function space. This, like, it's going to be a sphere, but projected to these two directions just looks like a circle. Okay, then we're going to have some teacher predictor here, and then we can see that the distance between these two are going to be the loss of the teacher. Okay, and then so now I'm going to show what the shrinkage optimality of the student looks like in this picture. So since the student is shrinkage optimal with respect to the teacher, one can show that it's actually going to be another sphere. Well, it's also going to project to a circle if I choose this projection correctly, but essentially the student is restricted to be in this set under this shrinkage optimality condition of the student. Okay, so the student predictor is going to be somewhere in this set. Okay, and then we can see here the lower bound immediately follows from just these two conditions. So the smallest error that the student can achieve is, well, the distance between the ground truth and this set to which the student is restricted. Yeah, then, well, one can show that this is actually the smallest distance that one can get. Okay, so this is the best possible student predictor as restricted with these two conditions only. Okay, so I'm not showing anything yet about how the student is trained, but we're gonna see that in a second. Yeah, so this assumes that the student has some like non-specific inductive bias, which means that 0 is sort of the effective hypothesis class of the student is going to be centered around 0. Okay, so here I'm showing the effective hypothesis class of the student. So it's going to be a sphere in some other norm. So like in the norm with respect to the student kernel, it's going to be a sphere. So then in this data norm, because like here, the distances are given by the data norm in this picture. So it's going to be some kind of like ellipse here. Again, then like the actual student predictor is going to be somewhere here, and it's not going to be the best student predictor. So it's going to be some other predictor. But inside this set that it's restricted to, and then inside the effective hypothesis class. Okay, so it's not necessarily the best, but it's still inside this green ball, so it's going to satisfy the lower bound. And then here I'm showing the gradient flow trajectory of the student. So it maybe it's going to look like some arc in this space, and like you can actually compute what exactly this arc is. So it depends on how this ellipse is aligned with respect to the ground truth here, which is given by how the student kernel is aligned with these eigendirections, or like how the eigendirections of the student are aligned with the ground truth, maybe. So in particular, if this ellipse, okay, so, and I'm also showing what the exitly regularized student would look like here. So there's some kind of not formal equivalence, but like similarity between like exitly regularization and early stopping. So it's maybe easier to see here what exitly regularized student looks like, because it's just a projection of the teacher to this ellipse. Yeah, but the gradient flow trajectory is actually going to be better here, which is non-trivial to show, but it holds. But yeah, anyway, so we see here that, so because like the student kernel in this picture, how I showed it, is not very aligned with the target. And we can see this because like this effective hypothesis class is not skewed towards the ground truth. Okay, so let me show you how an effective hypothesis class looks when the student kernel is aligned better with the ground truth. So this ellipse is now going to be sort of the longer axis of the ellipse is going to be closer to the ground truth. And then like maybe the actual student predictor is now like a bit closer to the ground truth than it was previously. Okay, and then we can also here show the gradient flow trajectory and the exitly regularized student. And so yeah, I guess this is for the case when the student's kernel is aligned with the ground truth more. Okay, but as I said, this is the case which we are assuming here when the student has a non-specific inductive bias. So the inductive bias is, part of the inductive bias is given by the student kernel. So the student kernel is aligned with the ground truth, but it's non-specific, so it's centered around 0. Okay, but then if the student has a strong inductive bias, so maybe it's like pre-trained towards like a specific model, f student 0, which now doesn't have to be close to the origin in this picture, then we can avoid this lower bound. So I'm going to show that looks. So for example, if we have a pre-training with a strong inductive bias towards some specific model, then the effective hypothesis class now is this blue ellipse, and it's much smaller than the previous green ellipse, because with pre-training, you're going to sort of run your gradient flow for much smaller time, or like regularize much less. So that's why this ellipse is much smaller now. Okay, and then, if this student predictor f is 0 now, that's pre-trained, is closer to f star, you can now avoid this lower bound, because now the shrinkage optimality condition is just another sphere that's now actually much closer to the ground truth, f star. And then, well, now the student error with some strong inductive bias, this LSI can actually avoid the lower bound. So this is what I'm showing the best possible student error in this case, and maybe the actual student error is going to be something bigger than that, but still can avoid the lower bound. Okay. Are there any questions about sort of this outline of the proof of the lower bound or the picture? What was shown here? Okay. And yeah, just a reminder, we had this general theorem that says that the student can zero out the teacher loss in target directions that are not aligned with the target. And this implied that for a ReLU network, the student loss is polynomial in the teacher with exponent 1.49, and in linear network that the student loss is quadratic in respect to the teacher loss. And both of these cases are stronger than PGR goes to 1. And then we also had this lower bound, which restricts the how good can weak to strong improvement be in this model. Okay. And just like a small comment at the end. So in both of these cases, we have both the student error and the teacher going to 0. Okay, but nothing from this lower bound restricts student error and teacher being sort of around constants as the teacher width increases. And so the question is, can we have maybe, like theta 1 behavior as the teacher width goes to infinity, but also still this quadratic gap? And yeah, it turns out that this is also possible. So in linear networks, we can come up with like a specific example that where the teacher is bounded away from 0, but the student still has this quadratic gap over the teacher. Then we just have to take some specific covariance here, essentially just make this eigengap large. Okay, and then if we take the teacher width appropriately, then we can get this theta 1 behavior of losses, but still a quadratic gap. Okay, and yeah, just a summary. We established that we can have weak to strong generalization in random feature networks. So I mean, this shows that this weak to strong generalization is not some kind of super intelligence phenomenon, but it's actually much more fundamental than that. And then in our setup, we had a non-pre-trained strong student, and this did not have any extra knowledge, but it had more features than the teacher. The teacher was trained optimally, both with infinite data, and we showed how this early stopping was crucial for enabling weak to strong generalization. And then we showed that this performance gap recovered measurement is going to go to 0, but actually something even stronger. We're going to have polynomial improvement, and all of this was provable. Okay, and then apart from that, maybe more interesting thing is this provable limit on weak to strong, so you can have at most quadratic improvement of the student. Well, in any linear model where the student is trained with gradient flow at 0, or more generally for any convex model class or regularizer. And the important restriction is that the regularizer is minimized at 0, which is this sort of non-specific inductive bias condition. And yeah, are there any questions? Not, yeah.
So I see that you basically have a two-step process, like estimator for the original function, right? You have the teacher,
yeah,
and then you have data from the teacher,
yeah,
and then that connects back to the earlier talk is about single index model. For the second stage, you actually have now a neural network also have well-defined features.
Yeah.
And then do you see the phenomenon as presenting the early work? You have this feature learning stage, and then if you keep going, you have overfitting for this type of a models, which is well-defined feature, but it's not a single index model.
Right. So in our setup, we don't have feature learning because the features are fixed and drawn randomly. But I guess it will be like an interesting future work to try to see if using those results we can establish maybe weak to strong generalization even with feature learn. Yeah.
have you tried real data to see the general phenomenon qualitatively, right? The second stage improves the first stage estimator.
I'm not sure if we tried real data for this setup. I don't think so, actually.
Would you think it would work?
I mean, I'm sure, yes, because under certain conditions where we would phrase this alignment of, ground, like phrase the alignment of ground truth with this eigengap condition as like a condition on like this real data that's being learned. So I'm sure like the same phenomena could happen under the right conditions in real data. I'm just not exactly sure what those conditions would exactly be. But
if you try, you will see it, right? Because you basically have two estimators. One is the teacher, and then you do the second stage, you have a student also estimator for the original true function or whatever for predictions. You can just compare empirically.
Right, yeah.
And that'd be interesting.
Yeah, I agree.
So I can start. So I want to make sure my intuition about these results, like generally speaking, what you've shown is correct. So in the linear version, you have this low dimensional signal, and vitally your student model has a bias towards those dimensions, right?
Right, yeah.
Like the kernel of the student model is more aligned with the true function than the kernel of the teacher model was. In the ReLU case, it's less explicit, right? But do you think it's a similar thing that's going on, that like the true function is kind of more aligned with this infinite ReLU kernel than with this?
Right, so in the ReLU case, I guess I didn't show exactly here in the presentation, but like when you write down what the kernel is, in that case, it also is gonna have some eigendecay, but the eigendecay is gonna be, maybe slower than what I chose for the linear network case. So then if your target function is spanned by like some finitely many, so in this case, EKs are going to be spherical harmonics. If you say, take your X to be uniform on a sphere, and then if your target function is spanned by like first K, first B to the K now, spherical harmonics, because now you're going to have this multiplicity and so on, then there's going to be an eigengap always after, spherical harmonics of order K and spherical harmonics of order K plus 1. And then just the eigengap is going to be, slightly different. It's going to depend different on this like D and K, but you're always going to have an eigengap at some point. And then you're going to be able to establish, weak to strong with the same sort of principles. Yeah.
Okay, that's interesting. Just kind of out of analogy, I've worked a bit on, lots of people have worked on self-distillation, where your student and your teacher are the same architecture, right? And in that case, as was mentioned earlier, you can do better than training from ground truth. And my intuition there, so like Peter has a nice paper about that being some kind of like iterative Hilbert space regularization. I think my general intuition there is that when you early stop the teacher, that like it's nicer to train when there's inherent noise. It's nicer to train on labels that are closer to the like Bayes predictor probabilities, not the sample, right?
Yeah.
And so here, there might be sort of an analogy in that you're.
Right. So I'm not exactly.
Well, the analogy, I guess, is just kind of what I said before. But I think this connection, like the fact that you still see this in population loss is interesting.
Right.
But if you did this on not population loss, probably you would have both effects going on.
Yeah. Maybe an interesting comment here is that so actually there's a typo here, but if I'm allowed to take multiple students, so in the lower bound here, I guess, if instead of just taking one student, so I start from a teacher and one student, and instead of that, I'm allowed to take however many students I want. The lower bound is going to apply as well with just the constant 1/4. So just taking like more students doesn't like help much, really. You're still going to be at most quadratically better than the teacher.
Yeah, but this
but I guess it's like not exactly
population risk based, right? Like when you have statistical error, it probably doesn't apply anymore.
Right. Yeah.
Any other questions? Right. Okay, so let's thank Marko. And,
Thanks. Oh, yeah.
oh yeah, by the way, there is a happy hour right after this talk. So between like 25 and 7 p.m. Yeah. So you can go to Free House. I think there is a group going from here.